November 7, 1940. Tacoma Narrows, Washington State. At 11 a.m., the third longest suspension bridge in the world began oscillating violently in a 42-mile-per-hour wind. By 11:10 a.m., the bridge was twisting 45 degrees in alternating directions, the roadway rotating like a corkscrew. At 11:10 a.m., the main span collapsed into Puget Sound, taking with it a car, a dog, and the reputation of the most celebrated bridge engineer in America. The disaster was not caused by a storm, an earthquake, or defective materials. It was caused by arrogance, specifically the arrogance of one man who believed he could rewrite the laws of physics. That man was Leon Moisseiff. The 1930s were the golden age of suspension bridges. The George Washington Bridge opened in 1931, spanning 3,600 feet across the Hudson River. The Golden Gate Bridge opened in 1937, stretching 4,200 feet across San Francisco Bay. These structures were marvels of engineering, massive steel towers supporting cables that held roadways suspended hundreds of feet above water. They were symbols of American technological supremacy during the depths of the Great Depression. Leon Moisseiff was the architect of this golden age. Born in Latvia in 1872, he immigrated to the United States and earned a degree in civil engineering from Columbia University. By the 1920s, he was a consulting engineer for the Manhattan Bridge in New York and had worked on nearly every major suspension bridge project in the country. His reputation was unmatched. Colleagues called him the Picasso of bridges. When the Washington State Toll Bridge Authority announced plans to build a bridge across the Tacoma Narrows in 1937, Moisseiff was the obvious choice for lead designer. But Moisseiff had a theory, a new approach to bridge design that he believed would revolutionize the field. It was called deflection theory. Traditional suspension bridges were designed with deep, heavy stiffening trusses running beneath the roadway. These trusses, often 25 to 30 feet deep, were intended to resist bending and twisting caused by wind and traffic loads. They made bridges rigid, stable, and expensive. Moisseiff argued that this rigidity was unnecessary and wasteful. He proposed that suspension bridges could be made lighter, cheaper, and more elegant by allowing them to flex. His deflection theory suggested that a flexible bridge would absorb wind loads by moving with the wind rather than resisting it, much like a tree bends in a storm rather than breaking. The theory was elegant. It was also catastrophically wrong. Moisseiff's design for the Tacoma Narrows Bridge were radical. Instead of a deep truss, he specified a solid plate girder only 8 feet deep. For a bridge with a main span of 2,800 feet, this created a depth-to-span ratio of 1 to 350, making it the most slender suspension bridge ever built. For comparison, the George Washington Bridge had a ratio of 1 to 47. The Golden Gate Bridge had a ratio of 1 to 168. Tacoma Narrows was twice as slender as the Golden Gate and 7 times more slender than the George Washington. It was essentially a steel ribbon suspended over water. Other engineers raised concerns during the design phase. Othmar Ammann, who designed the George Washington Bridge, warned that the girders were too shallow and would allow excessive motion. Theodor von Karman, a Hungarian aerodynamicist who had studied how fluids move around solid objects, cautioned that the solid plate girders would create aerodynamic instability. Moisseiff dismissed these warnings. He had calculated the deflections under maximum expected loads and found them acceptable. He argued that his deflection theory accounted for flexibility and that the bridge would be safe. The Washington State Toll Bridge Authority, eager to minimize costs during the lingering effects of the Depression, accepted Moisseiff's design. Construction began in September 1938. Almost immediately, problems emerged. Workers reported that the bridge deck moved noticeably even in light winds. During construction, before the roadway was paved, the structure would oscillate vertically in waves, creating a rolling motion that made workers nauseated. Some reported feeling seasick while standing on solid steel. The workers nicknamed the bridge Galloping Gertie because of its constant undulating motion. This should have been a warning. A structure that moves significantly during construction, when it is not yet carrying traffic loads, is exhibiting behavior that suggests fundamental design problems. But Moisseiff was confident. He attributed the motion to the incomplete state of the bridge and predicted it would stabilize once construction was finished. The bridge opened to traffic on July 1, 1940. The oscillations did not stop. On calm days, the bridge would move gently, rising and falling in smooth waves. Drivers reported the sensation of riding a roller coaster. Some found it thrilling. Others refused to cross. On windy days, the motion became more pronounced. The deck would rise and fall several feet, creating visible wave that traveled the length of the span. Local newspapers ran stories about the Galloping Bridge, describing it as an engineering curiosity. Tourists came to experience the motion. No one realized they were watching a structure in the process of destroying itself. Engineers installed damping mechanisms to reduce the motion. Hydraulic buffers were added to the cable anchorages to absorb energy. Tie-down cables were attached to the deck to limit vertical movement. None of these measures address a fundamental problem, which was not vertical oscillation but the bridge's vulnerability to a phenomenon that would not be fully understood until it was too late. That phenomenon was aeroelastic flutter. On the morning of November 7, 1940, the wind in the Tacoma Narrows was blowing from the southwest at approximately 42 miles per hour. This was not a storm. It was a moderate wind, well within the design parameters Moisseiff had specified. The bridge began oscillating vertically, as it had done countless times before. Drivers crossing the bridge experienced a familiar rolling motion. But at approximately 10 a.m., something changed. The vertical oscillations transformed into torsional oscillations. The bridge began twisting. Aeroelastic flutter is not resonance. This distinction is critical and widely misunderstood. Resonance occurs when a structure is subjected to a periodic force that matches its natural frequency of vibration, causing amplitude to increase over time. A classic example is pushing a child on a swing. If you push at the same frequency as the swing's natural period, the amplitude grows. Resonance requires an external periodic force. Aeroelastic flutter does not require an external periodic force. It is a self-excited oscillation, meaning the structure generates its own forces through interaction with airflow. Once flutter begins, it feeds on itself, extracting energy from the wind and growing exponentially until the structure fails. The mechanism works as follows. When wind encounters a solid plate girder, it cannot pass through. The airflow is forced to travel over the top and under the bottom of the girder. As the air flows over the top surface and under the bottom surface, it accelerates, following the contour of the structure. According to Bernoulli's principle, faster-moving air has lower pressure. This creates a pressure difference between the top and bottom surfaces. If the bridge deck is perfectly horizontal, the pressure difference is symmetric and the net force is zero. But if the deck tilts slightly, even by a fraction of a degree, the symmetry breaks. The windward edge experiences higher pressure, and the leeward edge experiences lower pressure. This pressure difference creates a torque, a twisting force, that rotates the deck further in the direction it is already tilting. As the deck rotates, the angle of attack increases, which increases the pressure difference, which increases the torque. This is positive feedback. The rotation accelerates. But the deck cannot rotate indefinitely. It is restrained by the suspension cables. Eventually, the cables pull the deck back toward horizontal. As the deck swings back, it overshoots, tilting in the opposite direction. Now the pressure difference reverses, creating torque in the opposite direction, and the process repeats. The deck oscillates torsionally, twisting back and forth in alternating directions. This is flutter. The critical factor is the velocity of the wind. Below a certain wind speed, called the flutter velocity, the aerodynamic forces are too weak to overcome the structural damping, and oscillations decay. Above the flutter velocity, the aerodynamic forces exceed the damping, and oscillations grow exponentially. For the Tacoma Narrows Bridge, the flutter velocity was approximately 40 miles per hour. On November 7th, the wind speed was 42 miles per hour. The bridge had crossed the threshold. The torsional oscillations began around 10 a.m. Initially, the twisting was small, only a few degrees. Drivers crossing the bridge noticed the roadway tilting but not severely enough to prevent passage. Leonard Coatsworth, a newspaper editor for the Tacoma News Tribune, was driving across the bridge at approximately 10:30 a.m. with his dog, a three-legged cocker spaniel named Tubby, in the back seat. Coatsworth later described the experience. The bridge was rolling gently when he entered, a familiar motion he had experienced before. But halfway across, the motion changed. The deck began twisting violently, tilting so steeply that he could not keep the car in his lane. The car slid sideways, scraping against the curb. Coatsworth stopped the car and attempted to exit, but the door on the driver's side was jammed against the curb. He climbed out the passenger side and found himself on a roadway tilting at approximately 30 degrees. Standing was impossible. He dropped to his hands and knees and began crawling toward the tower. Behind him, the car slid back and forth across the roadway as the bridge twisted. Tubby, terrified, refused to leave the car. Coatsworth tried to reach him, but the twisting motion threw him off balance. He abandoned the attempt and continued crawling. The journey took nearly 10 minutes. The bridge was twisting rhythmically, tilting 4 to 5 degrees in one direction, then 4 to 5 degrees in the opposite direction, completing a full cycle approximately every 5 seconds. Coatsworth described hearing the cables groaning and the sound of rivets popping out of the steel plates. He reached the tower and pulled himself onto the anchorage, which was stable. He watched as his car, with Tubby inside, continued sliding back and forth. At the same time, Professor Frederick Bert Fuckerhausen, an engineering professor from the University of Washington, arrived on the east side of the bridge. Fuckerhausen had been studying the bridge's oscillations for months, installing instruments and recording data. When he heard the bridge was twisting violently, he rushed to the site with a camera. Fuckerhausen decided to walk onto the bridge to retrieve Coatsworth's car and rescue the dog. This decision was insane. The bridge was twisting 4 to 5 degrees every few seconds. Walking on it was nearly impossible. Fuckerhausen made it approximately 200 feet onto the span before the motion became too violent. He turned back, barely reaching the anchorage before losing his balance. The footage Fuckerhausen captured is among the most famous engineering disaster films ever recorded. It shows the bridge deck twisting like a ribbon, the roadway tilting so steeply that the white center line is visible from the side. Cars that have been abandoned by their drivers slide back and forth like toys. The suspension cables, designed to remain taut, are slack on one side and overstressed on the other as the deck rotates. By 11 a.m., the torsional oscillations had been ongoing for over an hour. The steel in the suspension cables was fatiguing. Each twist cycle subjected the cables to alternating tension and compression, a loading condition they were not designed to withstand. Steel has excellent tensile strength but poor resistance to cyclic loading. Microscopic cracks form and propagate with each cycle, eventually reaching a critical size where the material fails suddenly. At 11:10 a.m., the cable on the north side of the center span snapped. The sound was described by witnesses as a gunshot. The deck, no longer supported on one side, tilted sharply and began to tear apart. Steel plates ripped along rivet lines. The roadway broke into sections. The center span, weighing over 6,000 tons, collapsed into Puget Sound. The collapse occurred in stages. The center section dropped first, pulling the adjacent sections with it. The structure folded downward, cable snapping in sequence, steel twisting and fragmenting. The entire process took approximately 30 seconds. When it was over, the main span was gone. Only the towers and the side spans remained standing. The wreckage fell into water over 200 feet deep. Coatsworth's car, with Tubby inside, went down with the bridge. Fuckerhausen's film captured the final moments. The footage shows the deck twisting violently, then suddenly dropping out of frame. The towers remain standing, but the roadway between them is gone. The film has been analyzed frame by engineers for decades. It is the only high-quality visual record of Aeroelastic Flutter destroying a large structure. Tubby, the three-legged Cocker Spaniel, was the only fatality of the Tacoma Narrows Bridge collapse. Leonard Coatsworth survived. Professor Fuckerhausen survived. Every human being on or near the bridge that day escaped alive. But Tubby, trapped in the back seat of Coatsworth's car, went down with the structure. Coatsworth later described his guilt. He had tried to save the dog but could not reach him without falling off the bridge himself. He watched helplessly as a car, with Tubby inside, slid back and forth during the final minutes before the collapse. When the bridge fell, the car disappeared into Puget Sound. Divers later located the wreckage on the bottom, crushed by falling steel. Tubby's body was never recovered. The story of Tubby became symbolic of the disaster. Newspapers ran headlines about the dog who died on the Galloping Bridge. School children wrote letters to Coatsworth expressing sympathy. The dog's death humanized a tragedy in a way that the destruction of 6,000 tons of steel could not. It was a small, innocent creature killed by forces it could not understand, a victim of human error and hubris. For Leon Moisseiff, the collapse was a professional and personal catastrophe. Within days, the Federal Works Agency convened an investigation board to determine the cause. Moisseiff was called to testify. He arrived at the hearings looking frail and shaken. He was 68 years old, and the disaster had broken him. Under questioning, Moisseiff admitted that his deflection theory had not accounted for torsional oscillations. He had calculated vertical deflections under static loads, but had not considered the dynamic interaction between wind and the bridge deck. He had assumed that flexibility was inherently safe. He had been wrong. The investigation board's report, published in 1941, was damning. It concluded that the collapse was caused by aeroelastic flutter, a phenomenon that was poorly understood in 1940 but that Moisseiff should have anticipated given the warnings from aerodynamicists like Theodor von Karman. The report stated that the solid plate girders created a bluff body that could not allow wind to pass through, resulting in alternating vortices forming on the downstream side. These vortices, known as von Karman vortices, created oscillating pressure fields that interacted with the bridge's natural torsional frequency. The report recommended that all future suspension bridges use open trusses or aerodynamically shaped decks to allow wind to pass through the structure rather than being forced over and under it. The recommendations also called for wind tunnel testing of bridge designs before construction, a practice that was not standard in 1940. Moisseiff never recovered from the disaster. His career, which had spanned 4 decades and included some of the most famous bridges in America, ended in disgrace. He withdrew from public life and died in 1943, less than 3 years after the collapse. Colleagues said he died of a broken heart. More accurately, he died from the stress of knowing that his arrogance had destroyed a bridge and tarnished his legacy. The engineering community absorbed the lessons of Tacoma Narrows slowly and painfully. The collapse challenged fundamental assumptions about bridge design. Engineers had believed that suspension bridges were inherently stable, that making them lighter and more flexible would improve performance. Tacoma Narrows proved this was wrong. Flexibility without adequate torsional rigidity was a recipe for disaster. The immediate impact was a shift in design philosophy. The replacement Tacoma Narrows Bridge, completed in 1950, used open trusses instead of solid plate girders. The trusses allowed wind to pass through, eliminating the aerodynamic instability that destroyed the first bridge. The new bridge has stood for over 70 years without significant motion. Other suspension bridges built after 1940 incorporated aerodynamic shaping. The Severn Bridge in the United Kingdom, completed in 1966, used a streamlined box girder designed to minimize drag and prevent vortex formation. The Akashi Kaikyo Bridge in Japan, the longest suspension bridge in the world, completed in 1998, underwent extensive wind tunnel testing to ensure stability in typhoon conditions. These bridges exist because Tacoma Narrows failed. The collapse also gave birth to a new field of study, aeroelasticity. This is a study of how structures interact with airflow, how aerodynamic forces can induce motion, and how motion can change aerodynamic forces. Aeroelasticity is now a core subject in aerospace and civil engineering. Aircraft wings, helicopter blades, and long-span bridges are all designed with aeroelastic considerations. The equations governing flutter are taught in every engineering school. The collapse has been called a successful failure. This phrase, while seemingly contradictory, captures a paradox of the disaster. The bridge failed, but the failure was so thoroughly documented, so widely studied, and so clearly understood that it advanced the field of engineering more than many successful projects. Farquharson's film footage provided invaluable data. Engineers could watch the collapse frame by frame, measure the torsional angles, calculate the oscillation frequency, and correlate the motion with wind speed. This data was used to validate mathematical models of flutter, which in turn were used to design safer bridges. The wreckage itself became a research site. Divers recovered sections of the collapse span and examined them for signs of material failure. Metallurgists studied the fracture cables and found that they had failed in fatigue, not from a single overload. This confirmed that the collapse was caused by repeated cyclic loading, not by a sudden extreme force. In 1992, the American Society of Civil Engineers designated the Tacoma Narrows Bridge collapse as a National Historic Civil Engineering Landmark. The designation recognizes both the tragedy and the lessons learned. A plaque at the site reads, "The failure of the original Tacoma Narrows Bridge on November 7, 1940, had a profound effect on science and engineering. It remains one of the most celebrated engineering failures of all time." The word celebrated is carefully chosen. The collapse is not celebrated in the sense of being praised, but in the sense of being remembered, studied, and honored as a turning point in the profession. It is a reminder that engineering is not just about building structures. It is about understanding the forces that act upon them, predicting how they will behave, and designing with humility. Leon Moisseiff believed he could make bridges lighter, more elegant, and more beautiful by allowing them to flex. He was not wrong to pursue elegance. He was wrong to pursue it without fully understanding the consequences. The Tacoma Narrows Bridge was elegant. It was also unstable. And on a moderate November day in 1940, elegance met physics, and physics won. Tubby, the three-legged Cocker Spaniel, died because a brilliant engineer made a mistake. That is the cost of hubris. That is the price of ignoring warnings. And that is why, 8 to 4 years later, every civil engineering student watches for Kármán film and learns what happens when a bridge is too slender, too flexible, and too beautiful for its own good. The bridge galloped, then it twisted, then it fell, and the world learned.